Hello, I'm Graham Lewis, and in this short video we're going to look at calculating the standard deviation of some heights of bonsai trees. I have to be honest, I've made up this data because I wanted the numbers just to work out nicely, and we'll look at standard deviation as a measure of spread. So firstly, we've got this distribution of numbers, so heights of bonsai trees, so 5 centimeters, and then 9 centimeters and 12 centimeters. So the first thing to do is to calculate the distance from the mean. So I've worked out the mean, which is the sum of all the numbers divided by how many we've got, which is 14 in this case. And so I'm going to find how each number differs from the mean. So I'm going to do equals the cell, and I'm going to subtract it from the mean. But I want to cell reference that, so it's always 10. I could have written 10 in this instance, but I'll cell reference it just because that will help you in future if the numbers are horrible decimal, etc. So we get minus 5. So that's the distance of my data x1 from the mean. And then I'll copy that formula down, and it'll work out all of the differences. Now, the problem is, if we were to find the average, the mean of those distances from the means, they would cancel each other out. So somehow we need to make these numbers all positive to get an overall measure of spread from the mean. So there's two ways to do that. We could find the absolute value. We don't do that as statisticians or mathematicians because the absolute value function is a very complicated one because it's not differentiable at x equals 0. It has no slope. The slope is undefined when that's the v. So a nice easy way to find out the make these numbers positive is square them. So I'm going to square the difference from the means, and those are called the squared deviations. So I'm going to do the distance from the mean squared, and those are the squared deviations. You can see that minus 5, which was the distance of 5 from the mean, has been squared to 25. So all the numbers are now positive. I'm just going to pause the video and bring this into my OneNote. Hi, so here we are. So we now got, if I add together all of these squared deviations from the means, I get a sum of the squared deviations from the mean, so my xi's minus the mean. I'm going to write mean there for a minute. I'll come back why I haven't put in mu or x bar, but mean squared. And I get 136. So that's how the numbers, the sum of my squared deviations. So that's the sum of the squared deviations from the mean. Squared deviations from the mean. Now, what we can do with that number is divide by how many numbers we've got. But we have a problem, and here's what the problem is. So the problem is all in lies whether our data comes from a sample or a population. If it comes from a population, then we know the true mean. So if this was a population of bonsai trees, and I said the true mean I know is 10 centimeters, then I can use the formula here that the variance is sigma squared, which is the sum of xi minus mu squared over n. So we worked out that the xi minus mu all squared, if you remember, was, if I just bring that down, that was 136, the sum of that number, sum of all of these numbers. So 136 I can write here, divided by my n number, which I believe is 14. How many numbers did I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 trees. So 136 over 14, and that's called the variance. And the variance is a measure of spread. And so that comes out at approximately 9.71. But the problem is the units are centimeters squared. So it's a great measurement, but the units are centimeters squared, which is a little bit strange. And that's why statisticians and mathematicians take the square root. So we'll take the square root of that number, and then that puts it back into this formula. So if we have a population, then we can take the square root of the variance, and we have this number here is n, and this is mu. And we can take the square root, and now it's back to centimeters, and we've got a measure of spread, which is called a standard deviation. Remember, the standard deviation is great when you don't have outliers. If you have outliers, the mean gets affected and could be biased, and so you want to use the median and interquartile range. But if you've no outliers, use the mean and standard deviation, as it's a more mathematical measure of central tendency because it takes into account the size of every number. Let's have a look if it's a sample and have a chat about that. Now imagine I did, say, 6 samples, or even more, maybe 12 or 20. And every sample which has a number of bonsai trees in, so imagine every sample maybe has 14 bonsai trees in it, we wouldn't expect the standard deviation for every sample to be the same. Maybe we calculated in this sample 1 and the standard deviation was 3.5 centimeters for those 14 bonsai trees. Maybe in sample 2 the 14 bonsai trees had a standard deviation of 3.8 centimeters. We'd expect some variation. Now the problem is, for our formula for a sample to make sense in terms of making inference to the population, we want it to be an unbiased estimator. To make it an unbiased estimator, what you need to do is actually change the formula for the sample standard deviation. We call it S, or S with a little subscript X or Y, whatever you're using. And because now we're not using the true mean, because we don't know it, we're using an estimate, X bar instead of mu, you have to divide by n minus 1 for the standard deviation. And equally the variance formula without the square root will be the same. So that's really important, guys, that if you don't know the population and you're using the sample to estimate the population, you need an n minus 1 because you're using X bar as an estimate for mu. So the reason is you're using an estimate for mu because you don't know it. You can't use the real value because we don't know it because we're using a sample. Estimate for mu, and we call this, we have now n minus 1 degrees of freedom. We've got less degrees of freedom because we've had to use this estimate for mu, which you'll see in other statistical tests as well. So that's it. So going back to my formula, if my 14 trees were actually from a sample, I wouldn't actually know mu. I would know X bar from my sample. That's my sample mean, which would still be 10 centimeters. That doesn't change. But my sample standard deviation, which is Sx, not sigma x, would be the square root of the sum of the distances, is still 136. But now instead of 14, I divide by 13. And the reason we do that is this is an unbiased estimator. So let's just calculate that number. And there we have it, 3.23 centimeters. So just to recap, when we have a population, the mean is a Greek letter mu, and it's the sum of xi over n. When we've got a sample, we don't say mu, we say x bar, because we're going to use that as an estimate, and an unbiased estimate is actually the same formula, add together all your xi's and divide by n. Variance, we use Greek letters again, sigma squared. We find that squared deviations from the mean, xi minus mu, we know the mean. We sum that and we divide by n because this is an unbiased estimate because it is the actual true variance. And then we take the square root to preserve the units, and so it makes sense. Make sure the square root is all of that. This is where it gets a little bit complicated. If we have a sample, we remember we're using our sample to make inference about the population. So now we're using an estimate, X bar instead of mu, which means that we've got one less degree of freedom to keep it as an unbiased estimator, and then we take the square root of that formula to preserve the units. And that's it. Thank you very much. I hope that helps. If you enjoyed this video, maybe you'll enjoy some of my other videos. Have a great day. Statistics is a great subject. Enjoy learning it.